Hi, my name is Noah Gift, and today we're going to talk about how to use small data engineering to do things like low code, no code, also how to do optimization, and how to use things like AWS Step Functions to quickly build up a portfolio of work. And really, in a nutshell, it works like this. You have different cities, and these different cities, you're going to want to pick a route where you're going to minimize the total distance. So here we go, minimize the distance. And so how do you pick something, what kind of an algorithm do you pick where you can pick the smallest route? And there's a bunch of different ways to try to solve this, but the naive approach would be to try to figure out a perfect solution. And the problem with that is that there isn't a perfect solution for the traveling salesman problem. Instead, you have to use heuristics. And the interesting thing about a heuristic is that you're going to use something that works pretty well and then use that approach to solve your problem. So a good example would be if you said, I want to do a random start. So that would be the first thing to select. And then that would be part A. And then part B, what I want to do is pick the shortest path. And so every time you're selected, every time a choice is presented in front of you. So in this case, let's say we randomly start, this is city A, this is city B, and this is city C. And let's say you started right here. If the distance between A and B is 3, and the distance between A and C is 2, then the greedy algorithm, or the shortest algorithm here, we'll call this greedy, you would always pick that selection if you're presented with two choices. Likewise, once you get to C, let's call this D, E, and then F, you also could choose where you want to go. So here we go, C to E, this could be maybe 3, and this could be 4, and maybe this one could be 5. And so you would say, oh, well, I want to go from A to C. So that's the first step that I do. And then now that I'm presented with a choice again, I want to go from C to E. And so now we go E. And then how do you figure out what your result is once you get to the bottom, you just figure out the total. So right now, so far, we've had a distance of 2 and then a distance of 3. And so the total so far is 5, right? And so when you start randomly every single time, you're going to start at a different path. So let's say the second time you go, maybe you start at, this city, right? This could be the second place you start, and then you do the same thing. Every time you have a choice, you're given between 2 or 3 routes, or however many routes, you always select the shortest one. And then at the very end, you could have a whole list of different options. So you could have, maybe one route, you go A, C, E, I don't know where you go next, G, and then another one, it's, C, E, F, or G. And then let's say this one was 10 and this one was 12 and then this one was 14. All you need to do now is just minimize, and you can just say that I want to select the route that is going to be the shortest total length. And this is really the nature of how a lot of optimization problems work. And so we'll call this an optimization problem, is that if it is nonlinear, so essentially there's exploding complexity about how to solve the problem, you can solve it using heuristics, and in general, an approach like this is a reasonable approach. This greedy algorithm is randomly start somewhere, pick the shortest distance every time you do a simulation, keep track of all the different simulations you run, and then of the time you have, that's the other thing to consider with a traveling salesman problem, is how much time do you have to run your simulation. Let's say that instead of, in this case, there's only 10 cities or something like this, but you could have 1 million cities. If there's a lot of cities, then it may take a long time for each one of these loops to run. And so what you may want to do is say, listen, I'll run the simulations for 30 minutes. Once 30 minutes is over, then I'm going to look into all the different solutions that I came up with, and then I'm going to minimize and pick the shortest route, right? And so this is, in the real world, would work pretty well. This would be a pretty reasonable way to solve an optimization problem. And in fact, you could use this yourself with your own trips across the United States or Asia or Europe. You could just go through and pick all the distances between cities and then randomly select a bunch of different routes and then run a simulation that decides at the very end how long it's going to run, and then pick the shortest route. So this is a good way to think about this business problem is the usage of greedy algorithms. So similarly, we see something like this in the real world. And I'll give you an example. When I lived in, I don't like those checkers. Let's do this. So when I lived in San Francisco, one of the things that happened all the time was, and we'll say this is San Francisco, that it's a very windy city. And so a lot of times you have, routes like this, and then you have a street that goes like this, and then, you have another street that goes like this. And so you have all these different, kind of strange, routes. And if you were down, somewhere over here, let's say you're right here, and you needed to go over to this location to meet somebody for maybe a business meeting or something like this, and we'll call this the business, that you can also use greedy algorithms in real life. And in particular, one of the approaches that's a pretty good approach is if you're going to go, let's say, diagonal, like if you could fly, you could just kind of fly over this and go and go to this location. But we don't have right now the hovercraft technology yet, right? We have to use our feet and walk. And so there are a few different constraints. One constraint is that you're going to have to keep going, up and down, right? Because it's a windy path, so you're limited there. The other one is a lot of times when you get to an intersection, there's a light, and we'll just make this the traffic light here, that the traffic light, if it's red, then you can't go, right? And so now you have to think about it. Should you just wait there? Like if like you could wait there, but you have a choice. Do I go straight, but I wait for 5 minutes? Or since I have to go this way anyway, why not every time you are stopped, if the option is available for you to turn right because it hasn't gone past this, right? Like this would be the plane that we don't want to go past, right? Is this, we don't want to go farther than this, but if you're still anywhere this direction, why not just turn right if you're stopped, right? And that would be a great example of an intuition behind a greedy algorithm is, oh, okay, I'm stopped at a light, let's go here. And then maybe you just keep walking until, you now have another light. Now this light is telling you again, you can't go, but this light says you can't go this way. Okay, well then just go left. And then you go left, and then you go here, right? So you can basically take what's given to you and make the best choice given the constraints that you have. And that's essentially the greedy algorithm intuition. And what's and we'll call this greedy algorithm. And what's fun about it is that it works in the real world. Like you don't need to necessarily build out equations and lots of complicated algorithms for this. You just use your intuition, which is pick the best possible choice at a given point in time, and a lot of problems can be solved that way. So let's talk about one more greedy algorithm that comes up a lot, and this greedy algorithm is making change, and we're going to show all these in code as well. But this is kind of a famous one called the greedy coin algorithm. And in this particular example, let's say that you have a machine that you're building, and this machine will deliver sodas to people. Here we go. And here we go. We'll just do this soda machine. We have this. The soda comes out of here. Now, how do you choose, what coins to give to people? If you needed to write the code to give change, well, you don't want to run out of change. And so ideally, you would stock the most amount of the largest coins, because those are they take up the least amount of space, right? So, the options in a change machine, we'll say greedy coin soda machine. The options are that you would have 25 cents, 10 cents, and 5 cents and 1 cent. Now, in theory, you could put anything you want into this, maybe the change reservoir, right? You could put it any amount of coins, but these have the most value. And so if you're able to stock the most amount of these coins, then you'll have the most storage, right? And you don't have to change as much. So this is really also a storage problem where it's a form of compression, essentially. Like if you could store all pennies, and you could in theory give people change in pennies, but it would be 25 times less efficient at the worst case, because of the fact that the quarters are so much more valuable. So what you need to do is come up with some kind of a computer code that will allow you to give the highest coin first, so you can have the most storage in your change reservoir. That's right. So we'll say this is where the change is kept. So a couple things that we can think about would be, what if we always try, again, the biggest coin first, right? So we can basically say, while true, essentially try giving people 25 cents. As soon as the remainder that's left, so if the remainder the first time through is $1.51 is the change, for example, then you would have 3/4 that you would give to somebody, right? So you'd say, okay, well, let's take 25, let's divide it into 151, and so basically you would have 3/4, and now you've consumed all of the possible options to give somebody the highest amount of change, and there's a remainder of 1. And now you can just give the penny. So that's kind of the intuition, again, is that always divide it by the largest denominator you can. Now, if you went through and you tried after the 25 cents, the 10 cents, it would say, nope, 10 cents, this is bigger than the remainder, so we can't do that. We can't do the 5 cents. What's left? Only 1 cent is left, so we'll give the 1 cent change. So it's also pretty intuitive, right? Is every time pick the largest coin, try to put it into the change until there's nothing left. And then because of that really simple algorithm, you can store mostly quarters and actually have much less of the dimes, and even further, much less of the nickels, and then even much less pennies, because this is really consuming the most amount of operations are being involved with the higher degree of change. So that's really, again, the intuition behind these greedy algorithms. Again, walking, making change, traveling around the world. And fortunately, you can use these techniques when you're solving problems. And these are all forms of optimization. Now it works as well with machine learning. That's something to bring up, is that if you've probably heard of deep learning, a lot of people are doing things with deep learning, and so it's probably worth talking a little bit about deep learning as well. And so with deep learning, the basic intuition is that you're on top of a mountain, and there's maybe even a couple mountains, and so what is the way that you get to the bottom? And this right here would be the global minimum, right? So this is the solution to the problem. And so in this particular solution, we need to get there in an efficient manner. Now, if you're on top of this hill right here, and this is you as a person, you're up here, you have to pick how far you go down the mountain, and maybe it's in the dark so you can't see. Like how far do you go off the ledge before you start going down, right? This is kind of an optimization problem. Now, if you run and jump really high and you're a very good athlete, maybe what happens is you fly and you go all the way to the other mountain, and then basically you're in the same spot, right? And then if you jumped again and you flew, you could go back, right? And this would be essentially the learning rate that you're using to solve your solution, and you're picking something that's too far too big of a learning rate to solve the problem. Instead, you want to learn how to go down the mountain with the correct amount of steps, right? Like you want to go at least far enough, but if you go too close to the surface of the mountain, this could be learning rate is too low. Maybe there's a lake right here, and by hovering too close to the ground, you get stuck, and then you fall in the lake, and then you're basically this is a minimum, but it's not the true minimum, because you're definitely went farther down, but you're stuck on top of the mountain still, right? Let's say you're only half of the way down. And that's kind of the intuition as well with these deep learning algorithms. The way they work is that you're also doing an optimization problem, and you're trying to optimize for this solution, and the solution is the global minimum. And if you, depending on how you adjust the hyperparameters for deep learning, you can go back and forth and kind of thrash. Or if you pick too close of a learning rate to solve the problem, you are going to be stuck somewhere in a local minimum. You want to go to the global minimum. And in fact, let me share with you a concept that demonstrates this with deep learning. So there's a technology called TensorBoard Demo, and let's take a look at this. Let's see, TensorBoard Demo online. Let's see. Here we go. Neural network playground. So I'll throw this into a chat message here. And so this is a great way to play around with this concept, right? Because deep learning is an optimization problem. And again, if we look at this, this is really the basis of how deep learning solutions come up with their problem. Is either you picking too far of a learning rate, or you pick one that's too narrow. Ideally, you pick one that's just right, and then you slowly are learning how to go to the global minimum. So you can play around with this visualization, which again is no code, low code. So let's say that you want to solve this problem, which is you want to classify, these blue, you want to separate them from this outside data set. So how would you do this? Well, I could look here and just click epochs. There we go. And notice that it already did a very good job. And the training loss is 0.006. The test loss is 0.008. And let's keep running. Let's keep going. And eventually, pretty quickly, we can get, now the training is basically what you learned, and the test is what's actually been validated. So you can see it's slightly overfitting, meaning that it isn't generalized enough to potentially get to the perfect global minimum. Once it gets to 0 of test loss, then you know it's a perfect global minimum. But it's pretty close. So we can stop and we can say, look, we're able to train a solution that is very good, right, at separating these two data sets. Now, what happens, and it took, I think, about 1,000 epochs or so, right? So it took a while to get to the solution. So we can actually speed things up by actually going a little bit higher. So let's change the learning rate. So again, how much can I learn at the same time? Again, think about going down the mountain. So if we run this, notice that how quickly this thing comes up. There we go. Training loss is at 0. And it was able to very quickly come up with a training loss of 0. Now, we could refresh this and we could try even higher. So let's try this, 0.3. And if we do that, now notice that we're having some issues here. Eventually, though, it worked it out. But look, it's learning very quickly. And look, it's actually very low test loss. And we can see that, it's kind of stuck there, but it's extremely low test loss. But basically, it looks like we converged pretty quickly because we bumped up the learning rate. Now, the problem, though, is you can't do this forever. If I just go to here, it's going to thrash back and forth and it won't learn anything. So it's going to be very similar to this person hopping across. He's just jumping back and forth, and not getting anywhere. He just keeps jumping. Maybe he's a superhero and the superhero keeps flying back and forth and is not making any progress. So let's see what happens. We change it very high and we do this. You can see it does nothing. It's learning nothing. It's not coming up with the best solution. So I think that the main takeaway here is that any kind of an optimization problem, it's good to use some intuition as well as to use more advanced techniques, and you'll especially start to see this in this concept of deep learning, is that these kind of basic intuitions of, I want to pick something that's pretty good and I want to try to do simulations until I get to a solution that I can actually pick from. This is kind of generally a theme for a lot of what happens with machine learning, with business intelligence. So let's look at some of the code now. So if I go to this repo here and I go to operations research, I'll again share this repository. That there's a bunch of different examples that we could take a look at, and in particular, here's actually the way that we could run this. So if we look at this particular example here, you can see that I was able to write something that's a pretty good simulation of what, in fact, you could even use this yourself if you wanted to, is I say create a NumPy data type here, which is the city start, the city end, and the distance, and also the distance in integers. And then I just make an empty array. And then I have something that finds all the unique cities. I have something that is able to randomize the start city. So all I do is I say return choices. So that's something maybe I should just point out real quick. That's kind of neat about Python. Let's go ahead and do this, and I'll call this, let's make a new notebook, and we'll call this OR, call this operations research, and I can add a little bit of text here that says, randomness. And in this particular example, I can just say choices is equal to, and I can say A, B, and C, or D. Choices, that's not going to work because it's syntactically incorrect, like this. And then if I want to select a random choice, I just say from actually choice. Let's call this choice list, like that, and we'll execute that. And I say from random import choices. So this is a great way to do randomness in Python, is that you put things into a list, and then you can just randomly go through and select these. So you can say basically choices, and if we actually do the question mark here, you can even look at the documentation for it. So you can say, okay, I want to pick the population, and I can even select things like change the cumulative weights, and then I also can select K as well, so return a K-size list of options. So you could return back essentially more than one, and you could also add weights. So there's a whole bunch of statistical things you can do in here that are pretty neat. But basically, I can say choices, and then I just pass in choice lists like this. There you go. And then now notice what happens, right? And in fact, if I did this, if I could say for, basically, let's loop through it and say for blank, that basically says throw away of the loop variable because I don't care about it. In range 10, let's just loop through, right, a whole bunch of times and pick a bunch of choices. I could do that, and let's see what happens. I think I need to do print choices. Let's do that. There we go. So notice how it's randomly selecting things, right? So I think this is a really powerful tool that's very, very simple to code up in Python. And if you want to add a little bit of randomness into something, this is one way to do it. Now, keep in mind, let me just check this in for you. And let me just call this operations research notes. And then I can say file, save a copy in GitHub. We'll retry. And I'm going to put this into that operations research repo. Okay, let's go here. There we go. So other people can play around with this if you want. Now, this, and let me even make a, we'll just say, I don't know, for loop. That's one way to do it, but you also could do another way, which is we could also build a function, and we could actually do a generator function. And so we could say generator function yield forever, forever random. So how would we do this? Well, what we could do is there again is a choice list. Let's kind of build this from scratch. So we'll say fruit, and we can do this. We can say apple, and we can say pear, peach, and maybe cherry. And then now we can build out inside of here yield fruit like this. And what this fruit will do is we'll say while true for, and we'll call this fruits, for fruit in fruits, and we can even put inside of here as well, from random import choices. So we say for fruit in fruits, yield random, give me a random fruit. And actually, I don't even need to do a for, because all I need to do is I just need to say basically run forever and yield me a random fruit, just one of these fruits. And now all I need to do is just say for blank in range 5, print, and then we can just yield some fruits. Yield fruit, yield the fruit. There we go. And we need to, I think, put next in front of this, I believe. No, it takes here. We need to say, we'll call this fruits, because we need to first make an instance of it. There we go. I forgot for a second how generators work. So basically, I think we say for I in range prints fruits, and let's try this out. And then is it next fruits? Let's see here. There we go. It says name random from random is not for, oh, yield choices fruits. There you go. Okay. took me longer than I expected, but basically what's neat about this, actually I could be lazy here and I could even put this into a function, and I could just say random fruit, and we can just say number equals 5, and then we could do this, and we could just move this in, and then basically we would just say number, and then what's cool about this is now it's even less work, because all I got to do now is call one thing, and I just say random fruit, and I just say how many fruits do I want, and how many random fruits. Let's say 3. There we go. Well, now I want to do more random fruit. Okay, we'll just do more random fruit, right? And there we go, random. And let's pick this 6. Now we got random fruit. I gotta make sure I use the actual function name. There we go, random. And you can see it's going to do this forever and ever and ever and ever and ever. Now the reason it can yield this simulated value forever is that these 2 lines are kind of magic in Python, because a while true is essentially telling something to run forever. But the problem with while true is that they'll consume eventually all the CPU, right? Because if it's on a single core machine, it'll eventually just consume all the CPU and it'll run. I mean, people can write servers. Like if you were going to write a server in a very crude way in Python, you could use while true and build some kind of server from scratch that accepted, I don't know, socket connections or something. But in reality, you don't typically do this because of that fact that they run forever. But if you add a yield to it, what it does is it says, run forever, but only return one thing at a time. And that combination really is kind of tapping into the potential of what the function would do. And so it's really helpful for simulations. And so in this case, then I write another function that kind of taps into that simulation. And then what we do is I can just keep using it over and over again. There we go. And every time it's going to give me a random set of values depending on how many pieces of fruit I want to select. And again, we can go through here and say random 2, right? And they're all going to be just random, whatever it is. Every choice will be a random choice. So I think that this style is a very good style to consider. Now, I think we could even, in this particular example, notice that it has the option of k equals 1. you in theory could even make it return additional values. I guess we could try that real quick. So if we go through here and we say from random import choices, let's do this. Let's just make a note, like mini fruit, and we could say from random import choices, we could make the fruit here like this, and then you could do something like this, for blank in for blank in range 5 choices fruit, but in this case we say k equals 2, and then we can print it out. So in theory it should give us 2 choices, and there we go. So it picks randomly 2 choices at the same time. So it is good to know about these little programming tricks here that can help you with simulations, because it allows you to write random simulations for some kind of an optimization problem that you're working on. In fact, I'll save this inside of GitHub here so you can take a look at this and play around with it yourself. So here we go, and we've got the random. So again, this is basically the point in this particular example. And then this one is pretty neat, because it just figures out it sorts all of the different distances that I selected, and then sorts them by the shortest distance. And then this greedy path here, this is the part where it picks the shortest path. Every time I'm selected, I have an option, path 1, path 2. I look at how the distance is, and then wherever the shortest distance is, I pick that one, and then I append. And then here we go. We have total distance, and then at the very end, I also can sum the total distance of each one of the trips that I made. And then finally, because I'm doing many different simulations, right? Because I can tell this how many simulations to run, I would go through and I would pick the lowest simulation. So I think that I can actually play around with this real quick. Let's go to open this up. It's pretty simple. If I remember correctly, I can just go to something called code spaces. Let me see if I have an example of this. No, so I need to create a new code space. So I'm going to delete this one. And I'm going to say new code space. There we go. And we'll go ahead and create this. And now I can make this a little bit bigger. And I think we've talked about GitHub before, code spaces, but I really like it because it's really easy to work on your code. And if I say Python 3-m, or no, actually I think it's virtual environment. We say virtual environment, tilde venv, then activate, create a virtual environment, then source it, and then we'll source it. We'll say tilde venv bin activate. Perfect. And now if I say make install, this should install the libraries that I need, hopefully. It's been a while since I worked on this project, but let's double check everything works. And then in theory, this this particular function, which is greedy, this greedy coin, I should be able to run it. So this says unable to import NumPy. Let's double check that I've got the right. No, it looks like it should be working. So let's run this though. So we'll say greedy algorithm. Okay, so this does work. So we can see here that what happens is if I don't pass in any values, that it goes through and it does a simulation. Notice every time I run this, it gives me a different distance, right? In this case, this is a total distance of 143. In this case, it was 129. In this case, it's 131. And so what's neat about this, though, is I can just do this. So I can just pass this in. And let's go ahead and run this. Let's do /. Wait, this is greedy random, and we'll say 20. So it would go through, it actually ran 20 simulations. And then it noticed that the shortest distance of those 20 simulations was 128. Now I could do 200. Let's see what happens. It does 200, and now it's going to take a little bit of time. You can see that, in fact, that may be the global minimum, right? Or at least the global minimum that was the easiest to find. I guess I could even go crazy, and I could say, give me 2,000 simulations, right? And it could just go through over and over and over and over again, trying all these different things. Still, right, you see that 128. Now, if I added a bunch of more cities, it would be much more interesting. But if I just say 2 simulations, notice that it didn't find the global minimum. So again, I think the big takeaway here is that the simulations, along with greedy algorithms, along with randomness, are really good toolkits to solve a lot of just problems you face in the real world, along with real interesting problems that are helpful to businesses. That first one was distance the only factor. Yeah, for the traveling salesman problem itself, that's the only thing we need to solve. Is we want the criteria for this particular problem was to minimize the distance. And so I guess, I could go back to this. So like in this particular example, really there's only 2 constraints. One is how much time do you have, right? If you have an infinite amount of cities, which, depending on, or near infinite amount of cities, then your only constraint is going to be how much time do you have to do a simulation. And let's say you run a simulation for 3 days, right? It's like you could pick over that 3-day period, it maybe was able to run 100 simulations. That's really the constraint, is the time you have. And the other constraint is that you want to minimize distance. And so the time itself, the total distance, the time is a very different constraint, because it's going to depend on each use case. But in the case of the problem, the global problem you're trying to solve is, I want to go the shortest amount of distance because I'm going to save more money on gas, or I want to save money in time. And this is, I think, something that you see a lot in real world optimization problem is that you have to choose, not only the solution for the problem, but also what are the real world constraints of the problem. And let's see, another question here is, in a greedy algorithm, we make the optimal choice at each step or only for the overall optimal way? So yeah, in the greedy algorithm, like for example, in this particular solution, in general, a greedy algorithm is at its highest level would be, if given the choice between at each step or each iteration, this one is distance 3, this one is distance 2, always pick the optimal solution depending on what it is you're trying to solve. And this would be the distance. In the case of the coin would be a little bit different in that you always want to pick the largest coin. So again, step 1, you have two choices. You have a 25-cent piece to give back to somebody, or you have a 5-cent piece. Which one do you give? You always go, in this case it was minimize distance. In this one, it's minimize, or it's actually maximize the coin size. But it's really the case of picking the best choice at each step of the way. And if you then combine that with some form of randomness or evolutionary algorithm. And so that's really the other component, is that, if we go back here, notice that, and this is why simulations are so important, is if we say one simulation, it's true that we did the greedy algorithm, right? We picked the lowest choice, but look what happened. We had actually a very bad solution, right? It's 155 total distance. And so it's not enough to only pick at a step-by-step basis the best choice. You also need to have this continuity where you could do lots of different simulations. And so that's where the simulations come into play here, is that if you're able to run a simulation, you can pick from a multitude of different choices. And in fact, that's actually something that I believe that they do with Tesla. I think I mentioned I was there a while ago, and I don't know every part of how their system works, but let me tell you what I do know, or at least I can infer, is that they have their vehicles. Let's just make this the vehicle 1, vehicle 2, and they actually have a bunch of optimization problems. So one is that they want to make the best choices for the drive, right? So that would be the steering, and this would be the drive choices, but they also need to pick choices for the road. And so there's multiple different models that are being created, and apparently they do this thing where they do pathfinding, and they don't yet know what is going to be ahead of these cars, and so they actually anticipate what the turns would be and where the road will go, and so they will predict this route. And so one of the things that they do is, as they're working on these models in the factory, they will actually push the models out into production environments, and they'll actually run in something called a shadow mode. And so what I'm assuming they're doing is they may be actually running a whole bunch of simulations, just like that, simulation. And then what they may be doing is, if they have, 100,000 vehicles, that potentially they're able to run 100,000 simulations. Again, it's in shadow mode, so it's not really running. And then they could pick, let's say, the best pathfinding algorithm, right? Because they're able to run all these simulations, and then now they take that and then they put that back into their system, and then that eventually would then go out into production, and then that would be their new production mode. So at a high level, this concept of simulations with greedy algorithms can also go into the real world. The other thing that they do as well, and again, this is the actual shadow mode, but they also have they actually have computer vision simulations where they're making essentially a model of the world, like a computer game, and then they're also will simulate different environments that are basically fake environments, and then those environments will also go through and they'll measure what happens. So this concept of simulation really is an important concept outside of just computer science and solving algorithms like this. But when you're implementing a real world solution, you may also need to have these raw ingredients like greedy algorithms, optimization, simulations, and also randomness, like how you want to introduce randomness. These are all almost like you're cooking to create solutions, and these solutions all come in very handy depending on what kind of problem you're solving. So another question is, are we going to get different results every time we click run? And so in this particular example here, if we were going back to the neural network, is that yeah, there is actually randomness associated with this. It's non-deterministic. But some of the things that you do here, once you've fixed down the different learning rates, they should be, I believe, reproducible, if I recall correctly, because they're able to, I believe, use some kind of random seed so that it's able to completely simulate what happens. Now, in the real world with real data sets, there is going to be some non-deterministic aspects of whatever algorithms that you're using. In the case of this, you are always, if you keep running this over and over again, you're going to get a different solution because there's randomness built into this. So that's maybe the kind of the formula for optimization is, again, greedy algorithms with a little bit of randomness, and you are going to get different results every single time, right? It's all completely non-deterministic, and eventually you just pick the right one. And yeah, another question here is greedy algorithms, isn't that just a number of simulations? So no, it's the combination of both, right? So it's really the if we go back here for, how would we do simulations for optimization? It's really it's a meta level. So it would be meta operation. So meta operations. So basically, each one is its own world that we're running simulations in. And then at the bottom, so here we go. Here we go. Here's the simulation. Here we go. In each of these worlds, there's really two things that are going on. Is that, in all of these, we'll call these are basically a parallel universe, right? You could say this is universe number one, universe A, this is B, this is C, and this is D. And in order to do that, we say we want a greedy algorithm, which is really a step-by-step approach, step-by-step. But then in order to, like, if we always did the same thing every single time, like if we always started on maybe this city, which is city A, then we would never get different simulations, right? And so that's really the problem. And especially it becomes apparent when you get a lot of cities, is that you're not able to really capture enough of a signal in order to pick the lowest possible simulation. So you need to run lots of different simulations here in order to pick the lowest solution. So step one is greedy, and then step two is some kind of form of randomness. Now, it could be there also is evolutionary concepts, and I believe there's libraries in Python that allow you to build some kind of other non-deterministic behavior inside. But the core concept is you do want to figure out a way to not just do the same thing every single time, or you're not able to leverage that global knowledge, right? The global knowledge of every one of these universes is running a different form of a simulation, and you want to globally solve to get the global minimum. So yeah, another option would be this evolutionary algorithm. And in fact, I think that Python, if we look at this real quick, Python evolutionary algorithm, I think there's a library, distributed evolutionary algorithms. So this would be something that allows you to use this for simulation. And there's, I think, many of these libraries. And so you could see how this would work. You could say, in this example, import random. And then this one says how simple it is to implement the one max problem with genetic algorithm using this DEAP library. And so you go through here, you import this, and then you basically create like an evolutionary type algorithm to solve a problem. So there's even more advanced concepts beyond just regular randomness, and I think the evolutionary one is a very interesting one to figure out how to solve an optimal problem. So I think you could even do things like figure out maybe mutations of viruses, or what is the optimal investment strategy, or there's all these different things you can do when you start to get into simulations. And in particular, this evolutionary computation framework could be a good place to start. So I'll just go ahead and throw this in there, maybe put a link to it as well if we want to link to this code. Let's see here. If I just open this up, let's just add this, and there we go. So we can just add another link here. Now I also could show you that was the simulation, but what about the greedy coin algorithm, which I think is another interesting one. So let's go ahead and take a look at this one. And let's look at this greedy coin solution. And so this is kind of a similar notebook where, how do I run randomness? We already explored that. It's pretty simple. How do I yield lazy infinite random? We already covered that, right? Here's the fruit example. But what if I want to go and build something like a web service that returns back something with a greedy algorithm? How could you do this? Well, one way to do this would be to build something that looks kind of like this. And then here's a function that is similar. So let's go ahead and take this function and let's look at it. So it takes an amount, we turn it into a float. It has a residual value, so that's essentially the remainder. And then, the result value. We have the coins, we look up the coins, and then we basically just consume them as they're coming through. And then we use that remainder to show us which coin we should pick. And so as long as the remainder is greater than 0, then we keep getting coins until there's no large coins left. But we always start with the largest, right? And we just pop it. So we basically remove the coin. So if I run that and I say, here we go, $11.34, we can see that there's basically 45 quarters, 1 nickel, and 4 pennies. If I say $1.34, there's 5 quarters, 1 nickel, right? If I change it to $1.36, right, or 36, right, we can see that it's going to give 1 penny. But in general, this is the concept of a greedy algorithm is being, greedy, like you would be at Thanksgiving or some large meal, all you can eat. Like when I was in Shanghai, I went to many restaurants where all you can eat seafood, which was very delicious, right? They have sushi, they have all kinds of seafood. You just keep eating. You just keep eating all the food. Same with the greedy algorithm, is you're eating all this food, you're eating all this thing, that the most you can get at the same time, and it works out well in this particular situation. So one of the things that you can do, it really does lend itself to building microservices, and this is an example of a microservice that we could build that gives us back the correct amount of change. And so I'm going to go ahead and grab this, and I'm going to go to AWS Cloud 9 here, and I'm going to log into this service. No, actually, I'm going to log into AWS Lambda first. So let's go ahead and take a look at this service. And whoops. Okay, so if we go to Lambda, and I can create one. And we go to Python and we call this change example, greedy change example, like that. I can just paste this inside, and I believe this should be pretty easy to demo this. So I can just, if you have never played around with Lambda, it's a place that on the AWS cloud platform where you can just paste code and then run it in association with some web service. So if you were going to build a back-end system for, again, a vending machine, this could be a great example. So let's go ahead and paste this in. And notice here it says import JSON and import decimal. And all we need to do is capture this event, and inside the event would be the change amount. And so I'll capture that JSON payload, and then I'll do the same algorithm that we just went through, and then I'll return back the response as a JSON payload. So let's go ahead and deploy that. Let's test it by adding an amount, and we'll just say, I think it's going to be amount, and we can say $1.35. Let's go ahead and format it. That looks good. Create it. If I test it, you can see that it returned back 5 quarters and 1 dime. So now we have actually a production web service. And what's cool about this is I could actually hook this up, I believe, if I say add a trigger, I can trigger it into a web service like this. And then we would say create an API. And then we want to say open. And let's go ahead and do this. And I believe what's successfully added, the function is now receiving events from the trigger. And then in theory, if I click on this, it won't work because I need to send it a JSON payload. And so then I could, use some other library or something like this and give it a payload. Let's see if I could do this real quick. So what I could do is I could go to Cloud9 here, which is their shell-based environment, or I could even use the Cloud Shell, which actually, let's try that. It might be easier. But basically, we're going to invoke this thing remotely via Python code. And one of the ways to do that is to use a library called Python requests, which we can pretty quickly test out whether it works properly. Let's go ahead and test this out. But that's the other thing to remember is once you start building these services that you may be asked to put those into production. And once you put them into production, they get a little bit more difficult to run. But if you're using a cloud-based environment, they can be really straightforward to interact with. And that's why I like building things with AWS Lambda, is that it, again, is a pretty straightforward way to build functions. And let's just try this real quick. Hopefully this wakes up very quickly. It's waking up our Cloud Shell environments. Okay, there we go. And if I say IPython, I could do, hopefully the request library is working. Okay, so I'm going to say URL like this, and then I could say requests.post URL, and then I could say, I believe if I do a question mark, it'll show me JSON data. I want to put in data. So let's do that. Let's do requests post URL data equals, and we can say amount, and then do $1.34. So if we're lucky, all this will be easy to do and it'll just work. And then we can say results equals, and we say result dot, let's see, I think it's result.json. It should return back a JSON payload. Okay, so it didn't, something's misconfigured, but it would look something like that if I wanted to invoke it. I don't know why it's not accepting this JSON payload, but it is a fairly straightforward process to kind of wire that up into a web service. Now, another way to wire things up into the cloud here would be, and let me just delete this thing or something, because it's, yeah, delete it. It didn't work, so let's delete it. But there's also something called step functions, which also work very well with building these kind of solutions. And on AWS, if we look and we say create a state machine, the concept is a pretty simple concept, is that you can visually define your code. Let's go through here. And you can see that it basically gives you this, like, again, this is a no-code, low-code solution where you're essentially building a state machine. And this works very well for simulation. So let's start with this. This is a hello world. You say you start, you have inside of here, the state is pass, and then you go to the end, right? So it's pretty simple. Let's go ahead and just run it, just so you see what it's like. Right, it gives you some plain text here, start, hello world, end. And then if I go to the end here, next, my state machine, it gives me the options for what to do with it. And then, well, let's change it, my state machine 2, and we'll run this. And then we can start execution, and then basically it runs it. And right, this is a very simple hello world, but you can put an input and you can have an output. So again, this works really well for starting to build some kind of simulation. So let's build one a little more complex now. We can create a state machine, and we'll say next, we'll visually define it. And let's do this. Let's say instead, let's throw this in there, and then we'll say this lambda, and then we'll get rid of this one. We don't care about that one. And what we can do is for the input, we want to, well, first choose the right lambda function. So we can make a new one. We can go back to this lambda here and make one that's like a more generic lambda function. So let's just call this coin example, and there we go. Let's just say Python, and I believe I think we could just still put that other example in, if I remember correctly. Let's go ahead and try it. So if we go through here, let's paste this example in. I think that this would work. So we go here, paste this, we deploy it, we test it one more time. Amount, just double check it all works. 135. Okay, create this, test it. Okay, so that looks like it works. So this one is called coin example. So we would go back to the step function and say coin example. And we should be able to, 50 function names found. Let's say enter function name. I think I can actually just throw, let's grab this, copy ARN. How about that? View function. Okay, good. So we got that thing in there. And then the JSON you want to provide to your Lambda as an input, use state input. So we'll go ahead and do that. And then at the end, we'll just go to the end. And then we'll go to next. And so basically, this is a hello world. We're invoking this, accept a payload. And that's how our system works. Okay, that looks pretty good. Now, in theory, we can say invoke coin like that, and then go ahead and create a state machine. And so we say start execution. And this is where I would now put in the payload to send to it. And I think we can just say amount and then do 134. So again, and this may or may not work, but basically, it looks like it did work. Actually, we got a little bit lucky. So look, here's the input. The output is this, right? It returned back this payload, and I think I could even change this so that it doesn't return back all that JSON payload here. We could change it if we go back to the code. Let's actually just have it return back the results instead. So let's just say results, return back results. Let's try that. Let's test it or deploy it, test it. There we go. So that's what it comes back with. So if I go back again to the step function, in theory, I could invoke it again by saying start execution, saying amount, and saying 134. And then start execution. If we look at the Lambda function, the input was this, the output was that, right? So again, what's pretty cool about this is that if you wanted to build a very complex simulation, like the Tesla simulation or something, you could build each one of these optimization functions and start chaining them. And one thing goes in, another thing goes out. And in fact, we can even keep going. And so we could do even more. Let's just keep going here and say, okay, we drag this. We got one here. And then we drag, and you can actually go to all these different things that you start. You can build other step functions. You can call out to the glue system, which is a data engineering job. You can also call out to APIs. You can query the Athena system. You can build jobs here. You can put things inside of a database. I mean, there's a lot of stuff you can do. Call into the machine learning system, which is SageMaker. But in general, I think the best place to keep going, if we want to make it a little bit more complex, just to keep it really, really simple, is that we can actually build one more, and then we can delete this. And now for this function, so we'll call this one create change, right? And we'll call that and then the second one we'll say how about I don't know, like multiply change or something. And so all I need to do is make another Lambda function real quick. And so we got this Lambda which basically returns this. So I'm going to make one more, and we'll call this multiply change. And we can go to Python, go ahead and create this. Okay, and I believe we can just say something like this, like events, and we can just put a comment so I don't forget what the event was called. But it was, yeah, I think it's just I think it would just be, well, we could first we could actually just for fun, we could just say like prints got this event. And that's how I would probably start building this out. And then you could return back the event just to see what the payload looks like. And you could deploy it, you could test it, and just say like amount. And I think we can just do this. Yeah, there we go. Format JSON, create it. And so if we test it, it should just return back the same thing again. So that looks like it works pretty well. But what if I said, like events, we could do counts and coin is equal to events. So we could say count. See, count is equal to events. Would be values. Let me just look real quick. If I go to Python and I just say results is equal to this, so it would be results. Let's look at the type of it. It's going to be a dictionary, and so we would say values like that, or items. We say values.items like that. So it would look something like this, or would it be result dot? Like we can look at the values, keys. I mean, I guess I could do, makes it a little bit lengthier, but I could say keys, right? And then I could say result dot values, right? And I could just do that. Or I guess I could say let's say dot values, and we'll say 0, or this is this dot keys. We'll just say list. Let's do this. There we go. And then I could do 0, something like this, and then I could do times 3. I don't know, I'm just doing something. I would have to also make this an integer, and I could put this on the outside. Kind of a silly function I'm building, but there we go. Right. If I do something like this, let's go back here and put it in this. Right. So I just say that in this case it would be event dot keys, and we say triple, something like this, and then we say return back triple. I don't know. I'm just making something that's like a toy function. There we go, 3. Right. So it's really a silly function. All it does is take the amount of coins and triples them. But the point is to wire all this stuff together. So we have multiply, or we'll just call it triplet, right? So triple coins, right? And then we again go to this. So we just need to find that URI here. So I copy, or the ARN, which is the resource. We go here, choosing enter the function name, put that in. There we go. And then we want to say what's the payload? Use the state, right? So we want to enter a JSON object yeah, we want to take the state from the other function here. So we're going to go ahead and say next. Oh, wait. Do you want to see and fix it? Yeah, let's fix it. Oh, it wants us to, create change is going to be, we need to do that. So we need to go back to the other function because it needs two functions. And this would be the change one I just created. I guess we could say last modified to find the one. That's not helpful. Let's do this. And let's what was it called actually? It was called let me open this up real quick. Coin example. It was called coin example. Here we go. I just needed to find the right name here. So coin example, copy the ARN, go back here into this, enter the name, coin example. Okay, next. And so now we've got a start, which will accept some kind of payload. It will go through here, create this change, then return it to this other function that, again, we can look at it like this. It's basically this state machine that kind of goes through step by step. And then when we're done, we can actually say next, and we just need to call it something. We can say like a silly chain reaction like that. And then we go ahead and say next, create state machine. And then let's do an execution. So again, the execution is going to be the start of the chain reaction. And so we'll say amount. And then from here, we'll say $1.34. And then we'll say, look, it's running. Great. Here we go. Look, it did this. Look, it's still running this one. That's a little bit worrisome that is running, that's taking that long. Okay, so that succeeded. But look, we can see the input is this. The output, right, is it gives us the correct change. Now we step through, we go to here, and look, remember we told it here, it's just going to triple this. So if I go here, it's going to triple it and go there. So this is a very, very silly example that doesn't really do anything useful, but it's a good example of the kind of chained reactions you can build. Especially, again, this is I would call like a no-code, low-code solution, right? Because it's a very, very tiny amount of code that you could use to build a simulation. And so, there's many things you could do with this. You could do traveling salesman problem, simulations, self-driving car solutions. And again, you can really, really quickly build things. And in fact, what's kind of cool about this, look, it itself has a simulation system here where you could actually go through here and notice that they let you, do their own simulator. So this is a very, very helpful tool for building simulations, right? And so this is just giving you some examples of how you could build things. So I think a lot of the things that we talked about are very useful. And let's maybe wrap things up here. And in a nutshell, let's go here. Let's make a new sheet. That, what are the tools of a productive person who wants to add value immediately to their company? So we can say the business analytics for people in a hurry. Business analytics for people in a hurry. So a few things to consider would be that maybe using the cloud can be very useful, right? Because we see how there's high-level tools in the cloud. Another one is to consider using no code and also using low-code solutions. Right? These are very, very helpful no-code solutions. Another one is that simulations, right, can be very, very helpful, especially if you use those simulations along with things like greedy algorithms, randomness, or evolutionary algorithms, and then also that you're able to take that simulation and run it somewhere, like run it easily without doing a lot of work to build things out. So I think these are just some ideas for how someone could get a job in a new organization, and within just a week they could start adding a lot of value if you use the right tools, the right approaches, and you're very, very efficient. It can be very helpful to an organization.